When you picture Venus, you probably imagine a 900-degree hellscape choked in sulfuric acid clouds. However, that is not what the data from Venera and Magellan actually shows about its first 2 billion years. The modern baseline remains undeniable. The surface temperature averages 465 degrees Celsius, hot enough to melt solid lead. At the ground, an atmosphere of 96.5% carbon dioxide exerts a crushing pressure 92 times greater than Earth's, matching the destructive force found nearly a kilometer beneath our oceans. In this heavy environment, the planet spins backward on its axis, rotating so slowly that one day drags on for 243 Earth days, longer than its own 225-day year. This extreme state is the baseline we know, but it is merely the endpoint of a catastrophic global collapse. Between 1961 and 1984, Soviet scientists and engineers launched 28 spacecraft to force this hostile world to answer back. 13 probes entered the thick atmospheric haze, and 8 achieved intact soft landings on the solid basaltic plains. The planet's actual state ceased to be a matter of theoretical modeling on December 15, 1970, when Venera 7 struck the ground at 17 meters per second after a parachute failure. Despite tipping onto its side, the armored titanium capsule transmitted 23 minutes of faint telemetry, confirming the crushing, lead-melting environment directly from the ground. 12 years later, in March 1982, Venera 13 and Venera 14 braved the yellow haze to capture the only color panoramas ever taken of the surface. These landers were engineered to survive 30 minutes, yet Venera 13 operated for an unexpected 127 minutes, drilling into the orange-hued rock before the heat and atmospheric weight crushed the electronics. NASA's Magellan spacecraft arrived in orbit on August 10, 1990, tasked with mapping what lay hidden beneath the opaque global cloud deck. Over the next 4 years, the probe used synthetic aperture radar to pierce the haze, mapping 98% of the planet's surface at unprecedented resolution. The resulting global mosaic exposed a world dominated by volcanic features, endless basaltic plains, distinctive ring-like structures called corona, and over 85,000 volcanic vents. But the most alarming geological revelation came from counting the planet's impact craters. Unlike the heavily cratered surfaces of Mars or the Moon, Venus possessed fewer than 1,000 impact scars, distributed randomly across its surface. This low density meant that the planetary surface was surprisingly young. It suggested that the entire planet had undergone a global resurfacing event between 300 and 600 million years ago. A massive surge of interior heat and lava had effectively wiped the slate clean, completely erasing the geological record of whatever Venus had been before. In 2016, a research team at the NASA Goddard Institute for Space Studies, led by Michael Way, converted these geological questions into a testable climate scenario. Using three-dimensional general circulation models adapted from Earth monitoring systems, the team simulated what Venus might have looked like billions of years ago. They built the simulation using Magellan's actual topographic data, but they introduced 2 variables, a shallow liquid water ocean and a slow retrograde rotation rate, matching the modern planet's 243-day sidereal period. Under a younger, fainter sun that emitted only 70% of today's solar radiation, the simulated planet did not burn. Instead, the model produced global mean surface temperatures hovering near a temperate 20 degrees Celsius. The key to this stability was the slow rotation rate. Because the planet spun so slowly, massive upwelling of warm air on the day side formed a persistent global cloud deck. This thick shield acted like an atmospheric umbrella, reflecting incoming sunlight back into space before it could heat the ground. According to these simulations, this protective feedback loop could have sustained liquid water oceans and a temperate climate for up to 2 billion years. If these models are correct, Venus was not merely warm, it remained habitable for a span of time longer than it took for complex life to evolve on Earth. This modeling does not prove Venus possessed oceans, but it shows that a wet, temperate twin was physically possible, operating under the exact same laws of physics that govern Earth today. Over billions of years, a gradual increase in solar brightness pushed Venus past a critical heat threshold. The sun grew hotter, slowly increasing the radiation streaming toward the Venusian atmosphere. As this solar flux climbed, the delicate equilibrium that sustained the planet's oceans began to destabilize. Rising surface temperatures forced liquid water to evaporate at an accelerating rate, filling the atmosphere with water vapor. This rapid evaporation created a devastating trap. As an exceptionally efficient greenhouse gas, water vapor absorbed and re-radiated the thermal energy rising from the ground. This extra trapped heat drove temperatures even higher, causing more ocean water to evaporate in a rapid, self-reinforcing feedback loop. The planet's protective dayside cloud shield could no longer reflect enough sunlight to compensate for the massive volume of heat trapped beneath it. As the oceans boiled, water vapor rose high into the upper atmosphere, far above any protective ozone layer. Here, intense solar ultraviolet radiation struck the water molecules, breaking their chemical bonds. This process of photodissociation split the water into hydrogen and oxygen atoms. Because hydrogen is the lightest element, the planet's gravity could not hold it. The solar wind and thermal energy stripped the hydrogen away, sweeping it permanently into the vacuum of space. Without hydrogen, the water could never reform. The oceans were permanently dismantled and cast into the void, leaving behind a dry, baking crust and a heavy blanket of carbon dioxide. In 1978, NASA's Pioneer Venus orbiter arrived to analyze the chemical composition of the thick atmosphere. Deep within the acid haze, its neutral mass spectrometer measured the ratio between normal hydrogen and its heavier isotope, deuterium. Because deuterium contains an extra neutron, it is twice as heavy as normal hydrogen, making it far more difficult for the solar wind to strip away into the vacuum of space. When a planet loses its water, light hydrogen escapes rapidly, while the heavy deuterium gets trapped, concentrating over time like salt in a drying basin. Pioneer Venus discovered that the deuterium-to-hydrogen ratio is roughly 150 times higher than that of Earth's oceans. This massive chemical enrichment is a planetary scar, the forensic fingerprint of a lost ocean. Without liquid surface water to absorb the planet's continuous volcanic outgassing, carbon dioxide accumulated unchecked, slowly building the crushing, toxic atmosphere that suffocates this world today. This planetary ruin serves as a direct warning. As astronomers search for Earth-sized worlds orbiting distant stars, Venus represents the real-world boundary of runaway greenhouse collapse. It shows how a temperate planet can cross an invisible thermodynamic threshold and become permanently sterilized. Yet, this reconstruction remains an active debate. Some researchers argue that mantle outgassing, rather than a primordial ocean, produced the high deuterium ratio. Others note that global volcanic resurfacing, dated between 300 and 500 million years ago, erased the ancient crustal record needed for definitive proof. To resolve these uncertainties, a new fleet of spacecraft will target the planet. NASA's DAVINCI descent probe and VERITAS orbiter, alongside the European Space Agency's EnVision, are scheduled to launch in the early 2030s. By measuring noble gases in the lower atmosphere and radar, mapping the surface down to the meter scale, these incoming probes will search for hydrated minerals and buried shorelines, testing whether Earth's evil twin was indeed once a temperate living ocean world. Venus remains a warning, not an anomaly. As we look to the stars for life, its scorched plains remind us how easily a planetary oasis can unravel. The boundary between Earth and its twin is terrifyingly thin. What do you think? Share your thoughts below.